Rob's currently at Microsoft Research, Senior Research Program Manager there, and he's been at Microsoft for about a decade, and before that got his PhD in geophysics at the University of Alaska Fairbanks, and has done quite a bit of research in remote sensing, glaciology, and is here today to discuss integration of technologies, and in particular the Microsoft Azure Cloud and into data science solutions. And with that, let's welcome Rob and let him get this laptop set up here.
And I'll just take a minute here to get everything put together. I hope. Precarious. All right, let's see how this goes. I've never done a IPython notebook-based presentation before. So let's hope that we run into some Python bugs and then we can debug as a community. Some local wildlife from up in the Pacific Northwest. And I do have a lot of things to sort of bring in and go through, so I do have a bunch of time here, and I'll try and take the admonition seriously and go slow and hopefully cover things well rather than a lot of things quickly. So yeah, I'm Rob Fatland. I'm from Microsoft Research, and part of my thinking about putting this talk together was sort of this meta idea. So just to give you my background, I started programming when I was like 12 by going into Radio Shack and typing programs into a TRS-80. So I've been fascinated with technology for a long time, and my career path has taken me into environmental science. So at Microsoft Research, thematically what I work on is trying to bring technology tools in to deal with just the sorts of problems we're talking about the data deluge and not being able to generate data but then never being able to look at it. So I do have a ready-to-go tool, in fact, to show you, and in fact one or two of them. So what I'm going to do is I'm going to sort of alternate between being a Microsoft hack and a scientist. And so I have two different IPython notebooks. One of them is in the folder, I think, if it's gotten uploaded. And the other one is not, but will become available. So let me see if I can drag those over there. So your job is to figure out which guy I'm being when at any given moment. Let me see if I can do this without screwing it up. Okay, so is that legible, or do I need to scale that down? I'm afraid I could not get this thing to double project, so I'm going to be craning my neck a little bit. Let's see. I'm trying. What's that? It looks legible. Okay, so let's see if I scroll down. We're running off the page. Zoop, zoop, zoop. Is that the entire width of the screen there working okay, or do I need to change the scale down? That's my question. Oh, this is going to be tricky. Okay. There's that. So that's the main address. That's the one that's available. And then this is the sidebar one. So there's that. Okay. So I'd like to start off by telling a quick story. In addition to doing the sort of job, I've also spent a fair amount of time doing STEM stuff, so just sort of freelance science outreach. And that's been in various different forms, but one of them has been doing science fairs. And one of the nice things about being a science fair judge is that you can sort of ignore the whole scoring business and just talk to the kids. So I'd like to tell you about a science fair that I went to once, and I was talking to 7th graders. And it's the usual kind of thing, you know, here's the experiment I put together, and sometimes you can see that they didn't quite get it, or sometimes they do get it. Sometimes their parents are involved, and so you sort of learn to look for that sort of thing. But this one particular young woman I spoke to, I went up to her and said, okay, tell me about your project. And she said, well, I got set up with a database by my dad, and I thought, aha, here's another project that Dad has done. And she said the database is stars, and I can scan through the stars by angle, and in any given angle I can count how many stars there are. And I said, okay, so she's really got the hang of this. And she said, when I do that I can make a plot, and here's some of the plots. And she showed these plots that had 2 bumps in them. And so she's doing great, and I'm like, wow, this is super. And I said, so what does it mean, the 2 bumps? And she said, well, the depth is unlimited when I scan across the sky. And so when I look in the plane of the galaxy, I see a lot of stars. When I look out of the plane of the galaxy, I don't see as many stars, and so that's when the bump goes down. So what I did was, I shortened that distance that I'm looking. And I shortened it and shortened it, and I kept making plots until the plots were flat. And when the plots were flat, then I figured that my sphere that I was looking at, or my disk that I was looking at, was entirely inside the galaxy. And therefore, that's how wide the galaxy is. And I'm like hardly following this because she's explaining it to me, and I'm like, and she got the right answer. So this is by far and away the best experience I ever had, you know, talking to a kid in a science fair. And for me, the main point is that she was able to do that because she was enabled by her dad with those tools, with that scanning tool. So she didn't need to know about SQL. She didn't need to know about any of that stuff. So we're this multifaceted community, and we're trying to work together, and some of us are hackers, and some of us are trying to work with the ideas. And I'm really a strong believer that it's easy to make a one-off tool, because I've made 1 million of them myself. It's much harder to make a tool that somebody else can use reliably, and because it takes more time and effort, and we don't have a lot of time. Time is all we have. So it's been really wonderful to see Python community as I've discovered it, kind of rediscovered it recently, and that penchant for doing that, for making tools that people can use, that sort of idea of, oh, I import anti-gravity and now I can fly. That's just, that's fantastic. And now I'll turn into a Microsoft hack. Microsoft gets it. Microsoft, the guys who are particularly working on the Microsoft Cloud. So I'm going to talk about Python as a new Python learner. I'm going to talk about the Microsoft technology stack as kind of an advocate and just sort of to give you a picture. So one of the things Microsoft is big on is calls to action. We have a lot of buzzwords. I used to be at NASA, and there was all acronyms, and Microsoft, it's all buzzwords. So the call to action for me today is to just sort of let this talk, you know, wash over you or whatever, but maybe just pick one thing, one term, one keyword, one something or other, and just go do search on it and spend 15 minutes figuring it out. There's probably a YouTube video on it. So it could be Azure Machine Learning, it could be, you know, the Azure Cloud, it could be Visual Studio. I'm a big advocate of that. And Visual Studio is the Microsoft development environment, I should explain. Microsoft has a lot of stuff that's Mac friendly. I think in this community we have a lot of Macs. I see a lot of Macs in the room. I use a PC, and one of the nice things that has come out of using a PC in Microsoft is sometimes we can only build one version of something in research. So the one version of something that we've built is called Worldwide Telescope, and it uses the GPU, the graphical processing unit, I guess, on my computer. And Worldwide Telescope is a visualization engine, so it's actually built for astronomy originally, but I use it for earth science. So this is an overlay from the system that I'm going to talk about, which is called Live Ocean. And up here is some cinematography, I think. So So if I hit play, then the camera angle changes, and you can just sort of start to see that there are these white overlays here. Those are little tracks, and I've decided that those are whales. So the grayscale overlay is chlorophyll concentration, and that's a forecast from a computational fluid dynamics model. And the whales just follow the local gradient as time evolves. So the whales are flying around and so forth. But the nice thing about this system, this visualization engine, is that I can pause it, and I can get rid of all this nonsense, and I can scan around and look at it from whatever perspective I like. And I can make time play fast and time play slow, and I can tell a story around it. I can overlay audio. I can include additional graphics and so forth. So this would be a potential visualization engine. And in my second IPython notebook, I have a whole bunch of references at the end, links actually, and that can link you over to learn more about this system if you haven't happened to see it. I spent a lot of time building a software library. It's called Narwhal, and it's intended for a developer to be able to make it easy to use the API that this engine has. And that allows you to import data in complicated and interesting ways. And you can also create reference frames that are Cartesian, and you can just drop abstract data in here and visualize that too. So it's got support for color and time and so forth. So I'm going to use it hopefully 2 more times to show a little bit more stuff. So that's that. And please interrupt me if you have questions about this stuff. One of the things I'm fond of quoting is that on my crummy little Lenovo laptop, I can drop a million data points in here fairly easily and scan through that. So I'll go back here. Okay, so the call to action is to go and potentially chase down one of the things that I talk about. And one thing I'm not going to talk about much is, hang on a second, I've lost my cursor. Okay, so there's that. There's our main guy. Okay. So one thing I'm not going to talk about much, but I'd like you to know about it, is that we have a lab in Cambridge, at Microsoft Research Cambridge, and those fellows are computational ecologists, and they build tools for themselves, and then they make them available. And the most relevant of those is called Fetch Climate. So Fetch Climate, I'm not going to talk about or display here, but it is a freely available service. It has an API, and it has a web interface, so you can either go there and do the click thing, or you can just figure out how to write Python calls against it. So it's a RESTful interface type deal. And the purpose of Fetch Climate is to aggregate a whole bunch of different climate data sets, including future forecast, so GCM models, and then to make that available to you at whatever resolution you ask for and whatever region of interest you ask for. And they have about 20 different types of data, so precipitation and humidity and temperature and so forth. And also things like elevation. So that resource is there, and if you're interested in finding out more, please come up and talk to me about it. So now I can actually start my talk properly. So here we have an IPython notebook. I won't try and execute my markdown, but I am talking about LiveOcean, and so the background on that will come up in a little bit. But I'm really interested in this. How do you figure out how to do something? As a new Python programmer, you're going to have to try and empathize with me as a new Python programmer. How do I get the basic structure of a loop and stuff like that, but how do I dig into things? So this talk will be a little bit of trying to dig into things, and maybe it will repeat things that have already happened, and maybe that's a good thing to have happen. Secondly, what's the value claim for the Microsoft stack? And for me, the main thing I would emphasize there is that there is a Microsoft cloud, and it's written by developers for the general public. Microsoft is later to the game than Amazon, so there's a great competition incentive. Microsoft is really trying to play catch up, and in doing so, they've created both the low-level services that you're used to. So the Azure cloud is the stuff you're used to. So it's Linux machines, and it's machines running Windows. It's your desktop. It's a server. It's a database. It's some storage. It's sort of that disk drive in the cloud, but it's a lot more than that. So A, it's the things that you're familiar with, and then B, it's sort of the combination of scalability and there's 3 here. Scalability and ubiquity, and what's the third thing? Intelligence. That's it, intelligence. So by cloud intelligence, I mean these higher level services that you can learn about and make use of. So it's not difficult to get locked into Azure and to sort of figure stuff out. They've tried to make anything you want to do something you can kind of figure out in a day. But if you were, for example, to generate a whole bunch of data, which we're talking about here, and send that into the cloud, you can actually create a little homunculus, a little Maxwell daemon to sit and watch that data flow by and look for conditions. And when a condition gets met on that data, then it can send you a signal or it can do something in response to that. So that's data analytics or stream analytics. And another thing that's really big is the Azure Machine Learning Suite. So I'll talk about that a little bit also. So that's the Microsoft stack. Oh, and the other piece of this too. Okay, so Azure, I'm jumping up and down. Good job. And then the other thing is, as a developer, I was used to using VI, the editor, or Vim now, and writing in C. And when I started working for Microsoft in 2006, I found out they had this environment called Visual Studio, and it just makes you a faster programmer, faster and a better programmer, particularly if you're getting into complex objects that have methods and stuff. Visual Studio knows about everything that's going on, and when you hover over stuff, it tells you what's possible. And so you can do that in Python, you can do that in whatever programming language, and it's very plays well with others, Visual Studio. It talks to GitHub, and it talks to Microsoft repositories in the cloud and so forth. So Visual Studio is a really great tool, and that's that. So relevant to geoscience, we have a number of projects that are sort of legacy projects, things that may start up in the future at Microsoft Research. I've mentioned one already, which is Fetch Climate. And another one is the one that's mostly the topic of this talk, which is Live Ocean. So I've jumped up and down about Microsoft and Python and Azure and Visual Studio. And the story today is based on my collaborations and my background in C and Unix and so forth. So here we go. Finally, we got to start executing code, but this is actually just hopefully code that, that's not good. Hopefully this is just code that we don't have to worry about for a while. Some of my recent work, so there's 5 things that are kind of informing this. Narwhal, I mentioned, that's software tools for people to do visualization in Worldwide Telescope. I'm a compulsive wiki page writer, but I'm also aware of how difficult it is to make wiki pages hold together when you're not working with 7 billion other people. But I've written a lot of sort of wiki documentation, so I have that mindset. I built a system called the Biogeochemistry data system to span the gap between geochemistry and molecular microbial ecology. So in other words, the microbial ecologists are out there looking at the ocean and trying to figure out what the bugs are doing and what genes are turned on and off. And the geochemists are looking at the dissolved organic matter and trying to look at the structure of that with big, huge mass spectrometer magnets. And so the two of them are trying to get together, so I built a system that's just going into a test phase. I won't share too much about that, except for one detail of it. But the point of that system is to sit in the cloud and allow people to publish to it and share their data. Microsoft technology, there's Live Ocean, which is trying to span the gap between research and public use. So this is the first time I'm bringing in actual public use of scientific data. That's another can of worms. And so I'll talk about that a little bit. And then lightweight data systems. That's something else I'm really interested in. I mentioned it to a couple people on Monday. If you are a scientist and you have a data problem and you're not necessarily a strong programmer, one of the things is how do I? What are the options that you have? So we got together at UW, University of Washington, and we had a kind of a 2-day discussion. And hopefully that's going to roll into additional discussions about this topic of lightweight data systems. So we want to tell people what are design patterns and what are good practices. So instead of dictating, use this file or use this library, we want to talk about what's a good way of going about it. And it could be solving your problems as simple as organizing your file system. It could be that there's this online service that you can just throw your tables into and start asking queries of it because it's sort of built to be using English and so on and so forth. So this idea of lightweight data systems will kind of come around again and again, and it's sometimes called long tail. But basically we wanted a scientist to be able to sort of survey what's possible and then do something effective in a short amount of time on a scale of hours to days to maybe a couple weeks, but not to have to engage in a huge, massive engineering task where you build something gigantic. Because if systems and organizations exist out there, then they should make it possible to sort of latch onto them and take advantage of what they already have going. Okay, so common to these efforts are two themes: Rob's Law. I modestly call this Rob's Law, and I'll tell you what that is in a second. And reproducibility, which is what I've been talking about, making tools that other people can use. Rob's Law is simply that Rob does not know what he's doing. I don't know what I'm doing. I don't know what I'm doing. So that generalizes, I've realized, to data. And my belief is that data is, generally speaking, acquired and generated not in the manner in which it is consumed. So if I generate data, I don't know a priori how it can be used. And if I make data available in a way that does not presuppose its use, then people can come and use it however they like. Okay, so I mentioned the Biogeochemistry data system for the Geochemists. I don't really need to execute this because the picture is here. This system runs and it generates provenance of what it does. So the idea would be that you would generate, let's say, 200 spectra and upload them to a system. The system will run some processing on those spectra and generate molecular formulas out of it. So it'll consolidate those 200 tables into one table. This is a little blow up. And then you can download the provenance and you can sort of see the workflow that happened to generate your high-level products, which are down here in the diagram. So the level 1.4 end result is a consequence of all these different things, and stuff is clickable and so forth. So data is private until you hit publish in this system. So now I'm talking about a geochemistry system for mass spec, FTICR mass spec data and fluorescence and so forth. You are contributing spectral geochemistry data from one of a small number of analysis methodologies, and you're getting some free value out of it. If you use the system, it does some processing for you. So there's a service there. That's the big problem, is if I build a wheel, who's going to come and use it, right? How do you incentivize scientists to actually come and use it? And it runs stuff in MATLAB. So if there's MATLAB code that can be compiled and run in a MATLAB compiler runtime, then the system can handle that. It can sort of wrap that up and execute. And that's good because a lot of people still write heavy-duty code in MATLAB. You can download particular results, and you can download this entire provenance tree. And then you can query your data across multiple data sets. That's something that's not easy to do if you're just working with spreadsheets. And you can query the public library. That's everything that's been made public. So all the people who've come in and published, push stuff into a public sphere, and then you can go and query that. And furthermore, you can send your results to other libraries. So if somebody else is creating a library where they're interested in a particular thing, you can just wire this thing into it and send it over. So we're trying to confederate. And then lastly, other libraries can dial in and make queries. So that's the idea, that we're not defining how you can talk to the system. We just create a query algebra or query logic. Oops, what happened? Now that's definitely way too big. I don't know what happened there. Okay. Okay, so continuing from my story about the girl who figured out how thick the galaxy is, and that she got there on the power of the tools built for her, this is sort of a meta digression on the culture and climate change. Around 2004, which happened to be when I was talking to that young woman, Naomi Oreskes published her Beyond the Ivory Tower paper, which is a study of peer review abstracts in relation to anthropogenic global climate change, and found that there was 75% support, 25% no comment, and 0 dissent, which we're all familiar with, but it was kind of a nice watershed event because it gave us a science article, a peer review article to cite to kind of try and put to rest debates about this stuff. And of course, that thread has continued on till today. We have the current administration talking about climate change as a real thing. And I mentioned that there's the Office of Science and Technology Policy attached to the White House, and they have started a climate data initiative and a climate initiative also. So they're occasionally making announcements about this can happen, and they're basically trying to put people in touch, put scientists and people with technological expertise in touch with decision makers, policy makers, people who are doing management of cities and that kind of thing. They're trying to basically be a brokerage. So whether or not this is going to work is going to depend on the stability of this platform, this OSTP message of let's try and work on resiliency to climate change. And then this room, if that brokerage worked, that building bridges across to people who can use the information, then this room and rooms like it become a really important resource for being able to work into the future anticipate what's going to be coming and start to get ready for it, and therefore mitigate the possible negative problems. So this is all stuff that you're well familiar with. Successful brokerage simply means being able to make those connections, and I haven't seen that happen successfully yet, but I see people working on it, and then a stability of the premise. But the final bullet here, and who's the information consumer, also gets to what I'm talking about in LiveOcean. That's the project I'm going to talk about, which is to say, again, I can't overemphasize that if you don't know in advance how your data is going to be used, if you are generating some really cool piece of intelligence, atmospheric, ocean, land, but you don't know who out there is going to be using it, then don't even try to build a way of using your data. Just think about the most general, abstract way that you can provide your data and stop there. So that was the philosophy behind LiveOcean. We tried to compartmentalize, or modularize is the right term to use, the relationship between the scientist and the end user. So I haven't even told you what LiveOcean is, so I should probably do that at this point. This is the region of interest. This is off the coast of Washington State. This is the Columbia River, and this is Oregon here. These are mooring stations, and then the red dot, those are the red dots, and then CTD stations are places where boats go, and they drop sensors through the water. And then there's some tide gauges. Okay, so that's something about a region of interest. And so enter LiveOcean. So finally we're at the topic of my talk. So after I get through this sort of introduction, I'm going to try and solve 4 problems in Python. I know the URL of an image, but when I display it, it's huge, so I want it to be smaller. I have a publishing my project problem on Azure. I heard about a website with an API that provides data. How do I talk to it? And then I got Argo data, which is some netcdf files, and I want to disassemble it and see what's in there. Okay, so actually I'm not going to quite get to my my LiveOcean intro yet, because I still have to solve this problem. I have no idea if that's going to work. Okay, this is working better. So digging down into code, some Python code. The problem that I had was, I described this a second ago. I have an image out there on the web. Its URL is some root, HTTP Stack Overflow image resize answer.png. Let's see if it fails or works. Okay, it worked. So if that worked, then this must work, right? Okay, so side message. I don't know if this has been brought up a million times, but the web is your friend. You can type any question you have about Python into a browser, and it will take you probably to Stack Overflow, but possibly to some documentation or something else. So the web is the genie. It's Aladdin's genie. It's just an information resource. In Bing, because I'm from Microsoft, Bing is a great search engine, I type Python image resize, and I get this Stack Overflow link, and it starts talking about, can I resize images in Python to given height and width? I use Python, da-da-da-da-da. And installed pill. Okay, so now I'm like, oh gosh, I now have to figure out what pill is. I barely understand Python, and now I have to figure out what pill is. Okay, well anyway, I read through this, and there's some stuff here. So how do I know that pill is the best thing I should use? What if that's some guy's boutique software? Once I install it, does Python know that the stuff is there? Now that I've installed it, how do I use it? If I have a bit of code that is useful, can I def it into a method and then use that, even if it has like these imports involved in the method? And then there's something called GCA and GCF that keeps showing up that has something to do with axes. So I'm really lost, and I just wanted to document that feeling of being lost. Okay, I'm not even going to answer these questions. I just sort of feel lost a lot of the time while I'm plowing through this stuff. So I started wandering around, and I arrived at this set of calls, and this really seriously took me like 2 or 3 hours, maybe 4. Maybe I'm not admitting it took me 5 days. But eventually it runs, and I get my figure, and I think maybe it's a different size. But I broke this up into some pieces. Oops. I don't know what's going on here. Okay. So to go against the finished result kind of thing, I want to just show a bit of the thinking here. So this actually works, but it makes the image really big. Here's this pill business. I think I'm still missing the edge of the deal. Is that true? There we go. Okay. So there's the IPython notebook stuff to make stuff inline. And then there's this kind of voodoo that I found on the web, which is sort of repacking things. And then you have to tell it how big to make the figure in advance, and then there's this image file that you're opening. And now I show it. And when I show the figure, it adds axes and a border around the outside. So then I have to go back and figure out how do I get, seems ridiculous. I'm resizing an image, but it's putting it on a chart like it's data. So am I doing this right or am I doing this wrong? And I make no claim that I'm doing this the right way. But anyway, then I finally get into this thing where these two numbers in parentheses, I don't know what that is. But I can resize the image eventually with this derived height. And now, finally at the very end, when I run this, it gets down smaller. So I've done this up above when I hit return. I made this little method called smim, which is small image. And it hopefully executes without giving me axes around the edge and without the border and stuff. And so I tried running it with these two parameters. There are two parameters to, come on. Both the sort of like the pixels dots per inch and then the size of the figure. And so I did a couple of examples to see how the choice of those parameters will make things blurry or sharp. So there's a sharp example, there's a blurry example, there's a big blurry. So I think I kind of have a method that helps me do this, but it was a lot of work and it's kind of goofy. Okay. So that was problem 1 of 4 to solve. And all I'm trying to do is sort of indicate the chaos, but the fact that you can go out in the web and get solutions and cobble them together given enough time. Okay, so live ocean. Jan Newton is a scientist at University of Washington, and she's interested in ocean acidification, sometimes called the evil twin of sea level rise. And that's impacting the ocean, it's impacting businesses. So if you grow shellfish, then you have to plant the baby shellfish, oysters at some point. And if you do that when the ocean is sort of down in a dip of acidity locally, then they won't be able to grow shells. So she commissioned she started off this blue ribbon study. They came up with recommendations, and one of those was, hey, let's build an ocean forecast system. So Parker McCready, who's another oceanographer at University of Washington, a physical oceanographer, applied to that and got funded. He runs something called the Regional Ocean Modeling System, ROMS. It's a computational fluid dynamics model. It runs on a Linux cluster. He keeps the cluster himself. He may at some point move that cluster up into the cloud, but for right now, he's just running on his own cluster. And when he runs for about an hour, and he covers that area of region of interest that we keep looking at. And he's not interested in higher level trophic stuff like big fishes and so forth. He's interested in the plankton because the plankton behave like water. They just go wherever the water goes. He's calculating where the water goes. So vertically, horizontally. And when that ROMS model finishes running, it creates about a 400 by 200 by 40 block of cells. So that now we're getting into net CDF area. In fact, that's the state of the water for 1 hour. And he generates 72 of them. So every day he can generate a 3-day forecast. And that's going to include pH, dissolved oxygen, temperature, salinity, and then these estimates of phytoplankton and zooplankton and so forth. So that's neat, but that's the science and the fluid dynamics. And the question is, how do we then connect that as is intended to a user community, to people who are interested in knowing whether or not they should plant their oysters today? And so this is just a color overlay of that same region of interest on a Bing map. This we've already seen. This is the capture of the whales running around gobbling up the plankton based on a guess that they're there. But how do you know? How do you know when you run this model that it's actually giving you something that's approaching reality? Well, that's what those stations are for, those validation stations. So there are moorings, and then you can go out and take data. But there's also this system called Argo that I'll tell you about in a little bit. But here's some early validation studies that Parker's done. And it's kind of fun to look at because, as you can see, the red is observation and the black is what the model predicts. So first of all, they have both about the same amount of spikiness, which is nice. And this is over the course of, looks like, 1 day. And there are places where they kind of match each other. And then there's places where the red spike goes way up and the observational spike goes way up, but the model doesn't predict that. But then there are other places, another one. There's other places where they actually track one another really well. So this validation study of the validating the forecast is going to be a really important part of what happens to live ocean once it stands up, because you have to know how good it is. But the initial indications are that the system, which Parker's been working on for like 2 decades, is actually quite good in many cases. And that means that you could do not only prediction of the pH of the water, but you could predict harmful algal blooms or just algal blooms. And you could predict where the currents are going. You could use this to perhaps save fuel if you're going out and fishing. And what I'm really interested in are the unanticipated uses of the data. And can you come up with a formula, for example, that mixes, let's say, an estimate of nitrates with pH and temperature, and comes up with an estimate of where some middle trophic level fish are going to be, because then presumably that's where the high trophic level fish are going to be, or where the whales are going to go, and you can go and have your whale watching tour become more profitable because you find more whales per voyage. So this is going to be a little bit kind of off the beaten track, this second problem that I'm describing, but it gets back to the sort of the Microsoft stack. So Visual Studio is free, it supports Python, has a rich set of capabilities, and as I was working with it on LiveOcean, I got this goofy error message. Okay, so I'm going to take a moment to digress to my other IPython notebook and talk about the Microsoft stack for a little bit, and that error will come up. So what is LiveOcean? Well, I've described to you the computational model that runs on an HPC cluster, and it generates these 72 hourly netCDF files that get pushed up to the cloud. So when they're sitting there in the cloud, nobody can see them, nobody can use them, and the end user, the person who would want to know what's in those files, is not at this conference. Doesn't know how to dig into a netCDF file. I barely know how to dig into a netCDF file. So what we did was we created a cloud solution, and it's a server that sits up in the cloud, and it's currently way too slow. But what it does is it listens on the internet for a request to come in. The request is in the form of a URL. So HTTP, LiveOcean, API, and it's just a string. And when that request comes in, that middleware goes and roots around through those 72 files and comes up with an answer and sends it back. Okay? So there's 5 different calls. There's get information, which sort of helps you bootstrap what the system does. But then there's get overlay and get value. So get value allows you to get a slice of data from the ocean for some particular parameter like temperature. And then get overlay allows you to get one of those PNGs and drape it onto a map. So ideally, somebody else, some third party, some company, let's call it Yoyodyne, comes along and they write an application for somebody that runs on their phone, so that their phone is just a tile that they look at and they say, yep, I can go fishing today, and here's where I should go. Okay, so that's the decoupling, the modularization of the design of LiveOcean. Scientist, fluid dynamics model, intermediate middleware layer in the cloud, Azure, serving through an API out to somebody who comes along with a client, and we don't know what that client's going to be. We just provide an interface to it. Okay, so let's see. If you were fast, you could have written down that key and then had a key to an Azure storage account. So I have to take that out because it's Parker's, and then I'll make this whole file available. So Visual Studio, now I'm being a hack again, so you can, that Microsoft hack. Visual Studio hosts your software, right? So you can put your software in the cloud, or you can do Git, and it just sort of works with that. And you can work with other developers on projects. It's all about big teams of developers, or 3 developers, working together on the same code, not stepping on each other, and being able to pass stuff back and forth. So it's a lot about software engineering, which if you're in the science community, it's kind of like, no, I'm just going to sit down and write my program. But if you start thinking in terms of software engineering and sort of bigger picture stuff, then you get the ability to make things that are more robust. So tools for managing that stuff, you can do things like backlogs, task lists, you can make charts of how your project's going. And then there's lots of different language support, including Python, and Visual Studio is free. So you can install the various different versions of it, and there might be a cost point, but basically if it costs you money, it ends up being like $200. But I think right now, Visual Studio is just kind of free. And then the last thing from a developer's point of view that I want to mention is Intellisense. So how many of you know what Intellisense is? Show of hands. Oh, okay, a smattering. So if you're working in Python and you have some instantiation of a class object, hopefully I'm saying that right, called Fred, then Fred can do lots of stuff. You can do Fred.paint the house and Fred.go get some groceries, parentheses, list of groceries. You can do Fred.fly fly to Chicago, you can do Fred. Maybe Fred can do like 73 things, and you like have a hard time remembering what those are. So in Visual Studio, unlike in, let's say, the VI editor, if you just hover over Fred with your cursor, this list pops up and tells you all the stuff that Fred can do. And you can select it, and you can easily start. You can actually start typing, and it'll tell you, oh, you're probably trying to do this method for Fred, or here's a set of things that contain the string that you're typing. Maybe this is what you want Fred to do. So it's really, really helpful in kind of acting like a super brain that knows what's going on. So Intellisense is pretty nifty. Here is an example of Intellisense where there's this parameter called parameter. This is in Steve Dower's presentation, where he's hovered over it and it's popped up the fact that the parameter is a float and it's an int. So in Python we have dynamic typing, which means the type of something isn't figured out until it shows up and you're setting it equal to something else. But Visual Studio knows that parameter can sometimes be a float and sometimes it'll be an int, because down here my func is calling 10 and the parameter is being passed in is 10, and sometimes the parameter that's being passed into my function is pi, is this floating point number. So the parameter can be either one, and Intellisense knows that, and furthermore you can like do a drop down and you can see under which circumstances will the float and which will the int be relevant. And so that's just kind of a starting point indicator of the kind of stuff that Intellisense can do. So then I want to make a point that if you have Visual Studio, there's a bunch of Python support, and two of those things are the Azure SDK and the Python tools for Visual Studio, PTVS. So I'm going to take a second and differentiate those two things because I get them confused. Okay. If you're going to use Python in Visual Studio, then you install these Python tools for Visual Studio, and the links are in this document. And that allows you to do all this Intellisense stuff. Okay, so that's just writing Python code in Visual Studio. Now, if you're going to work on the Azure cloud, then what you do is you develop code in Visual Studio on your local machine, or possibly on the cloud version of Visual Studio, but then you publish it to a place in the cloud. So think about the cloud as being a whole bunch of virtual machines that you can drop stuff into. So Visual Studio allows you to develop and test software, and when you think it's good, then you click the publish button, and whoop, it goes up into the cloud, and suddenly you can hit that cloud website, and you can see if your code actually does what you think it does. That's what LiveOcean is. So it's a Visual Studio project with lots of code, Python, it's built on Django, and then I hit publish, and up it goes, and then something goofy happens. That's okay. I can actually set breakpoints in the cloud instance of my project, and I can debug in the cloud using this Visual Studio environment. So that's the deal. The SDK, Software Development Kit, for Azure, for Python, allows me to do all this stuff. And that brings up the topic of virtual environments. So if you're putting one simple thing in the cloud, then it's not too complicated. But if you're putting several different applications in the cloud, and some of them use one set of Python libraries and some use another, then you need this sort of environment for each one of them. It's a virtual environment. It's not a real replication of the code just to save space. But it's a virtual environment that has to be turned on so that each of those individual projects has its own little Python sandbox that it plays with. So you're not clobbering namespaces and so forth. So it's just a code organizational tool. But back here, I was bombing along, and I got this error message: a virtual environment is required to deploy dependencies to Microsoft Azure websites. And I'm like having a hard time parsing this, and I'm scratching my head and searching things on the browser, and I don't know what's going on. But the solution turned out to be really simple. I had just accidentally turned off my virtual environment, and so it was trying to publish something without that organizational piece of machinery involved, and it wasn't letting me do it. So it's sort of taking care of me, even though I had to figure out how it was taking care of me. And I just found the little interface and activated my virtual environment again, and everything's fine. Okay, so I don't know what the point of all that is. But now we're back to problem 3 of 4, where I'd like to talk about writing against an API. So the API is the LiveOcean API, and it's very slow because it needs to be sped up. And there's good ways of speeding it up, but the first thing you do is you write the slow version of your code. So I'm just going to hit return a little bit. So this base URL is liveocean.azurewebsites.net. So this is actually something running in the cloud. And then if I tag on this API, then the code, that middleware, that LiveOcean middleware, knows that I'm actually about to make an API call. But there's going to be a bunch of stuff that comes at the end here. Okay. So I hit return. And now I'm going to hit return on this, and then as it's running, I'll scan back and forth and try and describe what's going on, hopefully. Okay, so this block of code is running. No, is it? Maybe it's not running. What did I just run? Yeah, no, there's an answer here. Maybe it just ran really fast. Okay, let me just scroll through it to describe what's happening. So, get value API call. That's one of the 5 different flavors of API call for live ocean. Again, this is a forecast for volumetric ocean off of Washington State. So I need to give it some parameters. I need to say when I want that forecast for. It's hourly, so it's going to be on June 2nd at 6 p.m. Zulu. And it's going to be at negative 10 meters, that's below the surface. Okay, so here's my call. This uses this requests library, which I imported up above. And I simply do a little bit of nesting URL voodoo, and I add on the parameters at the end. So now it's going to print out what did I send and what's the status of the reply. Okay, so let's go down to the printout. So what I sent was this. And if I went and pasted this in a browser, I should get the same reply back. And the reply is true, so that's good, and there's a good status. But you'll notice that the URL ended with the API, concluded with the API, and then I added the get value call, and then I added the question mark and the date and so forth. So this is an API call, and all I have to do in Python is format this string and hand it to something that knows how to send that as a request. An HTTP, I don't know, put or something. Okay, so then what comes back? What comes back is JSON. So has this conference addressed JSON at all? Not much. Okay, great. So JSON is still complicated, but it's closer to something that looks like Python. So JSON is like a dictionary of lists. It's something that comes back as text, and it's something that you can parse. You could either parse it by writing like low-level code, or you can go and get the JSON library, which is what I did. So there's a JSON library, and I converted the reply that I got back from LiveOcean into JSON. And so here's the JSONized get value reply is of type da-da-da-da-da. So I'm interested in the types of the data that I get so I understand what's happening. And that's of type dictionary. So I got a dictionary back with 3 elements in it. So I talked to LiveOcean. I said, hey, do a get value for me at this time and this depth. And what came back was a dictionary with 3 things. And the first thing that came back in the dictionary was called min value. I did some exploring to figure this out. And the third thing that came back is called max value. And it's a very big number, okay? And I asked, by the way, I didn't say this, the parameter that I asked for is salt. So that's the salinity of the ocean at negative 10 meters. Okay, so now I've gotten 3 things back, and 2 of them are just these floating point values. The third thing I got back is the data itself. And it's the data across that entire region of interest at negative 10 meters. It's salinity values, which in the ocean is about 32 on the standard PSU scale. That's parts per thousand effectively. And so there's a salt value, which is like that. And over here, there's a salt value, which is none, and that's because that rectangular box includes dirt, and LiveOcean doesn't know about the salinity of dirt, so it just gives me a none back. And then I counted out how many good values there were and how many nones there were, and they added up to the array size. So everything is okay, and my data array is self-consistent. So as an old array person, I've accomplished my main goal, which is I have a complicated data format, which might be netcdf, it could be JSON, it could be something, but I have an array I can index into, and that's this data array. So up here, there's the data array, and those look like 2 array indices, so I'm very happy with that. Okay. And so I'm sort of trying to learn the more advanced things about Python and dealing with arrays, but if I can sort of touch on something I'm familiar with, then I'm good. Okay, so this is going to take a while, and as it does, I'll explain Argo, and then I should also pay attention to my time. I think I have all of 12 minutes left, but that's okay. So this is a loop for x in range from the surface to 2,000 meters. So what I did was I picked a location out in the ocean, and I just started drilling down using API calls, and you're going to see how slow they are. And there's about 30 or so of them. And every time, so we're going to go down to 2,000 meters. We're already at 200 meters. So every time I do that API call, I get back that sheet of data, and I grab a value out of it. and I'm going to make a plot of the salinity with depth. And as you go down on the ocean, it's fresher water on the top, and it gets saltier as you go down until you get down to the very bottom, and it kind of flattens out down there. So hopefully, when it hits this plot command, we'll see something that looks like fresh water at the top and salty down below. And while that's finishing, I'll tell you about Argo. So Argo is a completely independent system. Argo is a drifter. You throw it out of an airplane. It looks like a skinny metal welding tank, like an oxygen tank. And it's often yellow. And it falls into the ocean, and it controls its buoyancy, and it goes down to 1,000 meters, and it hangs out there for about 7 days. And at the end of 7 days, it says, okay, time to get to work, and it goes down to 2,000 meters. So down at 1,000 meters, it's out of the way of the boats. It goes down to 2,000 meters, and then it slowly rises back up, and as it goes up through the water column, it measures things like temperature and salinity. Now, there happened to be, on June 2nd, an Argo float out in the bottom corner of our region of interest. So I went through yet more struggles to go and get that Argo data, and it's a netCDF file, lo and behold. So I thought, aha, what a great opportunity. I can sort of figure out how to parse a netCDF file and try and make a plot of salinity with depth on this Argo float. And I have a live ocean forecast, and I can compare the two of them. So that'll be cool. So how are we doing? So let's see, we have a couple more seconds here to go through this. Let me just ask, take a deep breath here. Let me ask, is what I'm talking about here kind of making sense more or less? Are there any questions at this point? Yeah.
So you got this many data generated by the ocean. Has anybody ever looked at the quality of that data, or is this automatic?
There's an incredible amount of work going into validating that data. So just millions and millions of dollars, because these Argo floats are all over the planet. And they are the reference data set for the water column down to 2,000 meters. So there's a huge amount of validation done, studies. I visited the lab where they build them the other day, and they just do just an enormous amount. So I'm sort of waving my arms, but by exhortation, I'm claiming that that's very, very accurate data. They just did a challenge to try and get down to like the third decimal point in measuring the pH of the water. It's one of those grand challenges. Yeah.
Just a quick technical aspect. You're getting this from this one Argo floater, or where in all? I mean, is that just because that happened to be what data was available on June
right.
2nd?
Yes.
Because I don't see any reference to a particular geographic location. It's just time and depth.
Yeah. So what I had to do is I had to go to some Argo sites. They're not really in the 21st century yet as far as data distribution. You can't do a search on an area. So what I did was I went to some sites and I did some kind of process of elimination searching until I found one. And then when I pulled that Argo data out, I actually unpacked it and found it records its own latitude and longitude, and sure enough, it was where it was supposed to be, so that I have a good comparison.
They move, right?
They move, yeah. They move like mad. They motor around out there.
They're not moors.
No, they're subject to the whims of the currents that they're in.
The thing, I guess the thing is live ocean, your live ocean Azure websites.net thing here. This is all there is behind live oceans. Is that correct?
What's behind live ocean is a bunch of initial conditions. So you go to the National Weather Service and you go and get stream gauge values and so forth. Then you run this 3-day simulation, and that says, for all the cells of water that I know about, here's my prediction for how much salt is in that cell of water at this time. So that's what the live ocean is. It's a prediction. And that prediction was made before the Argo popped to the surface and telemetered through a satellite its data back. And then now I'm going to compare the two of them.
I guess the thing I'm feeling confused about is the fact that running through your thing here, you went to live ocean and just said get value at a time.
Yeah.
And a depth and
right.
salt.
Mm-hmm.
That didn't give me any geography.
No, that's true.
Get me Argo, get me a location.
Right.
It was just,
so the Argo,
getting this set of numbers that I don't see any place where your API actually selected this particular data set out of live ocean.
right. So the API. So you're right. I'm kind of cutting to the chase with what I'm doing here. I'm getting a 2-dimensional array at some depth, and I know which index corresponds to Argo. So I'm pulling those values out. And I know where Argo is because of Argo's netCDF file. So I've created a correspondence, but I've done it by chewing gum and baling wire. And what I need to do is make this system be something that's operating, it can go and find those Argo things and say, hey, here's some Argo profiles, great, I can validate against my data record, and I can do that in an automated way. So that would be a future steps. So we're finished, and here at the surface, the salinity is low, 32 parts per thousand, and it rolls up to 34, so that's great. I'm going to skip the standard deviation stuff and just go down to the part where we deal with Argo, since we've talked about it so much. This is the Argo data set, and it's just sitting on my machine. So I'll make that available, and that's the Argo profile. So it also starts down around 32 and goes up to 34, so I'm really, really happy about that. It seems like one shot in 1,000, I mean, just sort of randomly picking this one correlation, at least it seems kind of close. But if we do a little bit more, oh, and this is just the metadata of Argo, so it's figuring out how to tear apart, oh, this is the project name, and there's the principal investigator, and so forth. But the real question is, do they validate each other? And that's what the overlay looks like. And I can grab this and drag it down. OK, so at least in this one case, I was able to show that the Argo data, which is the blue jaggedy stuff, and the live ocean prediction, which is the green thing, are similar to one another. And that could be done in an automated way as part of the validation campaign for live ocean, which would then lead the way to it being trusted in the public domain as an information source about the state of the ocean. And that could have impact on hundreds of millions of dollars of fishing industry. Okay, so with that, when I started to screw around with MetPy, but I didn't get anywhere. The last thing I'll mention is the Azure space in 5 minutes. Goes from the very simple concept of a disk drive in the cloud. So this is what a disk drive in the cloud looks like. You get an account. You create things called containers, which are like folders. And inside of that sits files, which are blobs. That stands for binary large object. And you don't tend to index into those the way you would on a file on a local disk drive. And then there's metadata describing them. And so here's all it takes to be able to do some stuff with Azure. I went to, this container name is F plus year plus month plus day. And it's one line of code. Blobs equals blob service. That's a Python library that I just imported. Storage and key, that's the location, and that's the magic key. And then it just gives me a list. And here's all these forecast lists. They happen to start at 002. You notice they're net CDF, and there's 72 of them. So that's the forecast for that particular year, month, and day. Okay. And then you can have, there are various tools. For example, this Azure Resource Explorer allows me to look through an application at my Azure storage. So this is day after day after day, and each one has those 72 files. Okay. And now I'm going to tear that apart, and I'm going to start doing this underscore dictionary keys and find out what's in my blob. Okay, it's got a URL and it's got a name. Well, let's print those things out. Okay, the name of the file is Ocean History 0002. So I'm just kind of playing around with exploring into what the Azure Python libraries give me. How do I tear this apart? The last one here, this properties, is some kind of object, so I'm going to do the same kind of trick on it, and I'm going to find out what the properties are and so forth. Okay, the last thing I'll mention in this talk, because it's been an awful lot, so I'll skip my other Python demo and so forth. I do have an example of from machine learning that, just in the interest of time, I don't want to run over. But I will say that if you are interested in exploring Azure, the low-end services, the stuff that I talked about, like Live Ocean just behaving as a server and blob storage and moving files around and making the responses to the API faster, that's kind of the low-level area. But then there's high-level stuff, and that includes something called Azure Machine Learning. Machine learning, if you're not familiar with it, is sort of the idea that a computer algorithm can learn and find patterns in data without being a priori told what to look for, using sort of generalized algorithms. And in this case, what I've done is included a screen capture of using the Azure Machine Learning Studio, where I've imported some, again, oceanographic data. This happens to be flow cytometry from a cruise across the Pacific. And I created a little workflow here. So if you're familiar with the lingo, k-means is a very common clustering algorithm. This is my initial data set, and I pipe both of those into what's called I don't know what that's called. It's too blurry, my printout didn't work. But it's basically a consolidating thing. It's building a model and applying it to that data and giving me a cluster. And that cluster, then I can simply right-click on that and download that as a CSV file. And then I can bring that into Worldwide Telescope and look at that, and it's 1 million data points, and I can drop it right in. So all these tools here comprise the kind of what you can do with Azure Machine Learning. And this is something that's I'm accessing through a browser, but there's a Go button down at the bottom, this run. So once I set up this workflow, I click on that Go button and it actually runs in the cloud. So you would not have to write k-means. You would not have to go find k-means. You just have to drag the k-means module and set the k-means parameters to run that against a large data set. Okay, so this is the Microsoft thesis, is that if there's stuff that's standardized, that's easy to do, we'll just build that tool for you, and then you don't have to. You can just go into the Azure Machine Learning Studio with your data set, and you can just wire things together and start exploring. There's a program called Azure for Research. If you go to that website, it's up here in this notebook, you can write a one-page proposal and you can get 6 months of Azure time. It's sort of, if you were to convert it into dollars, you could probably floor it and burn through $30,000 in 6 months if you were doing like really heavy-duty database stuff and so forth. But that's free if you write a good proposal and it gets approved. But it doesn't have to be a huge proposal. It's like a one-pager. So they're looking for researchers who want to get into Azure and explore it in a meaningful way. And that's what Parker McCready did with LiveOcean and with us. And then another scientist, a hydrologist named Anthony Arndt, came along and said, hey, I'd like to use Azure too. He got his Azure account. He saw the LiveOcean code base and grabbed it, and he adapted it to a hydrology model for the south coast of Alaska with glaciers and stuff. So the point is that the LiveOcean project that I've worked on with Parker will be open sourced. It's code that's available, and you can drop any kind of model data that you're interested in or any other kind of data that you want to serve out. It's a template for creating an API in the cloud. And so that's pretty much a high-speed tour of most of what I wanted to talk about. And so since I'm out of time, if there's any questions, great. And otherwise, thank you very much. I really appreciate the chance to tell you all this stuff because I think it's great. So thank you. Yeah, this happens to be a plaid grid, so it's structured, it's fixed. It's plaid because the spacing of the grid changes as it goes across. Some of the cells are wider or longer in latitude and longitude, and then the depth also varies from one cell to the other, but there's always 40 cells vertically. So the structure of the grid, you could go out and build it with rebar. It doesn't change dynamically.
I know some models use unstructured grids.
Yeah. Yeah, so that's getting into the mechanics of the fluid dynamics model. And you're right, there's a bunch of different ones. There's triangular-based ones. There's ones that can flex and stuff. And Parker can address that. I'm not good at answering that question. But I know that Parker kind of has worked on this really hard, and he's settled on this, so he likes it a lot. And he's an estuary guy, so he's trying to deal with the complexities of coastal. But you can... Yeah, oh yeah. That model goes all the way down into Puget Sound. And then he wants to re-implement this model at a finer scale just in Puget Sound and just in the Georgia Strait because you get better results if you can downscale. Yeah, that's true. But then you train kids to build Arduino devices and go out and float them around and use that for your validation. So, and then they end up talking to you at science fair. Yeah, yes?
Your telescope's pretty nifty. Is that a GIS? Is that a Google Earth? What is that?
Well, if you want to be competitive, you say it's Google Earth, but it handles 1 million data points and it has vertical and you can generate custom graphics. So it's a very powerful version of Google Earth. I've used it a lot, and so I'm accustomed to using it. There's a learning curve. There's resources for learning how to use it. It's free. It's now open source. The entire thing is open source. And basically, you could think of it as a powerful environment that harnesses your GPU and cloud stuff like the Bing Maps to give you good local texture. And you can do stuff. I've done everything from watching baboons ranging in troops across Africa to seismic events within the interior of the Earth and how that reflects the subduction plate boundaries to a lot of ocean stuff and so forth. So it's a very flexible tool. But it takes some energy to learn how to use it. But the sort of the starting point is you just copy a block of cells out of Excel and paste them in. And each column is like lat, long, date, depth, or altitude, or whatever. And then suddenly you can just drag a time cursor and you can see everything unfolding. So it's a lot of fun. Okay, I'll make my escape.
Thank Rob for